Thank you very much for the invitation here. So let me start by just fixing some notations and objects of interest for this talk. So F, we will fix F a finite field. And call P the characteristic of F. And take L a prime, which is different from the characteristic. X will be a smooth and projective variety over F. So to search X, we associate Chow groups as usual. And to understand these groups, we use cycle class maps. So in this case, for L-adic et al. Cohomology. So let me just make annotations for these cycle class maps. So we use the Chow groups of X with ZL coefficients, because the cohomology group has ZL coefficients. So the first cycle class map, I will denote it by CLI, which goes just to cohomology of X itself. Often I will omit this et al. Sign, 2I of I. Then we can go to the cohomology of the variety over an algebraic closure, X bar, C def I, fixed by the Galois action, of course, if we start here. And where J, so it's a Galois group of F bar over F. And the composition, I will call this class CI. Okay. So the Tate conjecture would say that these maps are surjective with QL coefficients. And in the integral versions, one is interested to know what can we say about the surjectivity with ZL coefficients. And one often usually looks also for the maps over an algebraic closure, which I will denote like that, which goes from Chow group of X bar. So X extended to an algebraic closure, again with ZL coefficients. And that goes to H2I X bar, ZL of I. And so because we've started with X bar, actually the image is in the union of fixed elements by all open subgroups. Open. Just for this talk, let me just denote this union for short. It's not, of course, a common notation, by UH2I XL. In the end of the talk, we will maybe use this notation just for short. So as I said, in the integral version, we will be interested in the surjectivity of these maps. So the related questions, which are surprisingly of some interest for informaticians. So I've been asked several times about that. So not to look, the first one is more or less the same. It depends on how do you look to this. It's not to look for the L coefficients, but just the map with finite coefficients. What can one say about this? So you see that it's almost the same thing. But still, you can try to do on this level. So these maps, try to understand them. And the second question, if sum of cokernels is non-zero, so these maps are present here, is not zero, then try just to compute. So if you feel annoyed during the talk but still interested, you can try to think on direct computations. So now let me just tell you which are some known results for for different values of I, some examples and counterexamples. Go there. So first, like some general properties. So the first one you would like to look for is starting from 0, so say 0 cycles. So let me just recall that in this case, the Langweil estimate says you that always X has a 0 cycle of degree 1. Okay. So Next is one cycles. Then for one cycles, we have the result by Schoen, which says that if you believe to the Tate conjecture for divisors on surfaces, then you believe that, then he proves that C bar dimension x minus 1 is surjective. Yeah, that I said. Yeah. I will always refer to Tate conjecture as to conjecture with the QL coefficients, and then if I want to make precise, I will say the integral version for the questions we're interested here. Is that okay? Is that okay? Okay, so let's look from another side. So there is nothing to say for n equals, for I equals to 0. So for I equals to 1, then you can write, so let me write it like that. Okay. So from the Kummer sequence, you can write that if you look to this map, and then if you look to co-kernel, this one injects actually to the Tate module of the Brow group of X. And that one, this one has no torsion. Just by the general property of Tate modules. So this tells you that in this case, again, Tate conjecture for I equals to 1 implies the surjectivity of CL1 and also C1 are surjective. So the next question would be to consider the case where when I equals to 2. So this is a case where one has some examples and counterexamples. So first, one can express the co-kernel of this class map, the torsion in the co-kernel. So this is precisely the point of the integral version. In a slightly different way, so this will be less about of the variety itself, but about the function field of the variety. So you can write this like, so this is like H3 unramified. I will tell or recall what is that. QL ZL of 2 modular its maximal divisible subgroup. So this is the result by Collet-Helene and Bruno Kahn. Where this group, this one is defined as a limit of the group with finite coefficients. And these groups with finite coefficients, you can view them just like where, okay, I did like this. This one. Oh, sorry? Yeah, I knew that you would object. Yeah. I'm just surprised that it comes 2 minutes after I said. So this group is just the set of classes in the cohomology, Galois cohomology of the functional field of X with these same finite coefficients. And the unramified means that the residues at all points of codimension 1 points of X is 0. So for any small x, a codimension 1 point of X. Okay, so this is for unramified, the classes which would have no residues. So anyway, this gives you the way to study these questions on cycles by just studying some questions on cohomology, Galois cohomology of the function field. So maybe let me tell you something about, well, why should I write it? Just here. Something about the size of these groups. So conjecturally, for I equals to 2, one would expect that, well, I hope that one would expect that this group is of finite type. As far as I understood, it's consequences of the Bath conjecture, but Bruno told me that not everybody believes to this conjecture, but well, let's just think that, say, it could be of finite type. And also conjecturally, okay, hopefully. So, and also conjecturally, this group with infinite coefficients at that time, so the whole group is finite. So, for instance, this follows from that one. And meaning that in particular here you can forget this maximal divisible subgroup if you don't like what is that. Okay. So this is also the related to the question to compute actually the co-kernel. So at least we know that it's finite. Well, anyway. Okay. And there is also some arithmetical issues also with this CH2. So well, going still on left. So arithmetical, meaning that assume that you have a fibration of a curve. Okay, this is a curve. We are still over a finite field, and we are interested to the generic fiber. Then, if the cycle class, yeah, that's one, dimension x minus 1 is surjective with integral coefficients, then the Brouwer-Manin abstraction is the only one for existence of zero cycle of degree 1 on the generic fiber, of zero cycle of degree 1 on the generic fiber. So I think that this result is due to Kato and Saito. Saito. Yeah. And so in this context, one could be interested to understand this cycle class map, and actually one can also find a formula which is similar to this one. This would be some group which generalizes somehow this unramified cohomology modulo its maximal divisible subgroup, but maybe I will not write it because it's anyway it's too difficult. It seems too difficult to compute. But just to say that also there is a way to express co-kernel of the class dimension x minus 1 as some unramified cohomology group, which will be, I can still write like just like that, H and in addition I forget X H n, which is analog, which equals, okay, I will write it like this, which equals to H3 unramified if n equals to 3. So I think that's enough. Okay. So if you want some details, just ask for this. Okay, so that's all for general, and now let me speak about examples and counterexamples for I equals to 2. I will just write it here, and then I will push back the blackboard. Okay. So results for I equals to 2. So let me start from positive ones. So essentially, everything what we know for positive results is for fibrations. And actually, there are two types of them. So the first one is if you take a fibration over a surface with a generic fiber conic. So in conics. So X will be of dimension 3. S is a surface, smooth and projective. Then the result of Parimala and Suresh says that CL2 is surjective. So this one, okay. And this is done by showing that H3 unramified is actually 0. Using also results on brow group of function field of S. This is due to Saltman. Okay. 1. The second positive result is for cubics in P5 with characteristic at least 5, which we did in common with François Charles. And in this case, we establish that C bar 2 is surjective. But we still don't know. So no, it's not right enough. So open. H3 unramified is it 0 or not? So we didn't manage to compute that. And okay, so this is done. I was speaking about fibration. This is done because we actually view X via Lefschetz pencil as fibered over P1. And then we use some analysis on this Lefschetz on the incidence correspondence and Fano varieties related to this Lefschetz pencil. Okay. It's just an idea. So like this, we view this like a fibration on cubics. Okay, so this is 2 for positive results and then negative ones. So the first negative, so it will be the third one here. It's also for fibrations, but for quadrics in higher dimensions. So if you look for X over P2 in quadrics of dimension 3, so the quadric of dimension 3, so X of dimension 5. Then one can construct examples where C2 is not surjective and the H3 unramified is non-zero. Here. So this uses lots of results on cohomology of function fields of quadrics in particular. So this is the first objects like fibrations. And then the second series of examples is for classifying spaces of algebraic groups. So let me give you 3 examples like that. So the first one is a classical result of Attia and Erzebruck, which was originally for the integral Hodge conjecture, but revisited by Totaro. So which gives actually a class alpha in UH4 of XL, so with this notation from the beginning, okay, such that L alpha equals to 0. So alpha is a torsion class, and alpha is not algebraic, meaning alpha is not in the image of C bar 2. Okay. So then we were thinking about a way to produce a class which would be also non-algebraic, but non-torsion in the sense that it doesn't die when we quotient the cohomology modular torsion. And so in this case, you can also use the classifying spaces of algebraic groups. But so here it is, sorry, I didn't say. So here the group is elementary group of rank 3. So just CL cube. And with Yagita, we used the same, more or less the same approach, but for other types of groups. So J of type, so I will make a list of types, and I will call this list T, because maybe we will use it again. So of type G2 for L equals to 2. So exceptional groups, F4, L equals to 3, or E8 for L equals to 5. And in this case, actually, this choice is just related to the fact that such a group has an elementary subgroup which is non-toral inside it. So that's why we look to these groups. And then one can show that there exists also, well, let me call it alpha again UH4X alpha L, such that alpha is non-zero if we quotient by torsion and non-algebraic. And finally, in the same series of counterexamples, there is also a result by Carmichael, which shows the same result as here. He constructs a non-torsion, non-algebraic class, but for all L, not only for L equals to 2, 3, 5. So he takes J equals to the quotient of SUL modulo the diagonal embedding. And then he shows that for any L, so for L like this, studying also the elementary subgroups inside of this group, there exists a non-torsion, I will write like this, non-torsion non-algebraic class. Non-algebraic class in H4. Okay, so this is all for like the list of results. So now I was intended to give some sketch of proofs, so some small details on some of them, in particular on this one for cubics and also for the classifying spaces. And I can also say some just 2 works on quadrics. So I just want to ask you by which question you want to start. The quadrics of dimension 3?
No, quadrics of dimension 2.
I think it's not clear. Well, wait. Quadrics of dimension 2. So you will have a 4-dimensional variety. No, it's not clear, I think, because for 2 cycles, so you cannot reduce to Schoen's result saying that it's 1 cycle. So no, I think it's not clear. No cohomological dimension. No, actually, well, okay, I can tell you this in this perspective. So one actually doesn't know any single example of a variety of dimensions 3 or 4 where one knows to compute this group, and this group is non-zero. So in particular, the one we thought quite a lot is you take a product of 3 elliptic curves, then you construct very easily some classes that seems to be that are unramified, but you cannot show that they are not zero. Okay, so we can discuss if you want. So no. So I still didn't get my answer. So or just I should just finish and just leave you for break.
Your choice.
No, it's unfair. It's not possible. BG. Okay. So let's start with BG. So for okay, I will still write here. Counterexample 4. So the point is the following. So as in examples of Atia and Erzebruch, you want to use somehow standard operations as abstraction for algebraicity. So the way you do this is as follows. So first, you observe that for X, a smoother projective variety over a field K, maybe K should be perfect or something like this, but anyway, or more generally for objects in a pointed motivic homotopic category. So here BJ lives actually. So for both of them, I mean, it's inside, you can consider the motivic homology groups like this. Or, so this is by with Nisnevich topology, and this one is with Etal one, which for smooth and projective varieties are quite well understood. So in particular, you have 2 properties here. So first, this is here. You have Chow group of n x mod L if m equals to 2n, and 0 if m bigger than 2n. And for these groups, so these series of results, I mean, it doesn't follow from definition, of course. So this one is hm et al. X mu L tensor n for X smooth and projective. Now, on these groups, one has several operations. In particular, one has the one which we'll be interested in Q1 operation. So maybe I can continue writing here. So Q1 goes from hm to n, okay, to hm plus 2l minus 1 n plus l minus 1. So now comes my favorite question. If alpha is in C in H, also so here or with etal version, or with etal. So if you take H in, no, sorry, it's not 2n, it's n. And here, okay, and if you look for 2n, n, then what will be Q1 of alpha? Yeah, you know? You know, I mean, of course you know. No, you have to just, I mean, it's very formal from what I said. So it goes, it belongs to H. So here I take 2n, okay? And if I multiply this by 2, I get something which is smaller than that one. So because we are with, in this case, so it's actually just 0. Okay, so this tells you that the consequence that if you manage to find alpha in, well, say like this, H42, because this will be the indices of our interest, such that etal, such that Q1 of alpha is not 0, then you will show that alpha is not algebraic. So this is just a strategy. And so now let me show you which how to apply this. Okay. So first, to right. Okay. So for J equals to this elementary group, one understands. So it's in particular it's explicitly written in the work of Voevodsky. Motivic cohomology with CL coefficients. I think this is the name of the paper. So then you can compute the cohomology of Bj. So for Bj, you have an explicit, so you have actually 3 generators and then Box-Time. So on these generators, then for Bj, one can find easily, alpha. Call this star, very fine star. So let me just tell you what I call, how do you view actually Bj, and how can you view these groups and as well as Chow groups for Bj. So this is a construction due to Bert-Totaro. As I will recall here. Okay. Okay. So then, for any algebraic group J, you just linear algebraic group, okay? So you just can put it in GL n for some n. And then in this way, you view J as acting acting on some W, like a linear representation. And then you consider an open here where the action is free, okay? With free action. And then you call S the codimension in W of the complement of W minus U. Okay? And then, so the point that one can show that for some nice functors, I will give examples, nice functors. And Bruno can tell you exact hypothesis for these functors. So for nice functors, even if you assume if S is big enough, then the value of F on U mod J does not depend on U ni on J. No, on J still on U or on U, yeah, on U on W. I mean, okay. So nice functors meaning that they satisfy some homotopy invariance and also some purity. And in particular, for this will work for F equals to CHI. I think that I should be just S should be bigger than R, or something like that. And then also for Cal cohomology or for motivic cohomology, if you want, okay, as well, in the way we define them there. So this is the way you can define you can define this classifying space. And actually, if you look to the paper of Voevodsky, it's not like, well, he has a proposition which says that it's the same. But as far as I remember, you look for simplician definition. And then you use some kind of change of topology map. So if it's like R alpha lower star for some alpha from Zinknes-Neves to et al. Or something like that. So anyway, for us, we can take this definition, yes. Well, you can compute them everywhere, and they're compatible somehow. And also, what also I forgot to say that you have a map here, which is just a change of topology map, and for these Chow groups, this will be just a cycle class map. Okay. Okay. Yeah, so that's precisely the point. Of course, they are quasi-projective, so we don't like this. I mean, it's not what we want. So let me show you how to construct, for instance, for J of exceptional or whatever, a projective approximation of these spaces in the sense that we want a projective variety which will have the same cohomology groups, etc. So this was the first part with the standard operations and the classifying spaces, and then second one will be projective approximation. Well, I should have said that there is a preprint of Equital on the of Thorsten Ekedal on the archive, with the title exactly projective variety approximation of classifying spaces or something like that, where he constructs this in a much more general setting that I'm going to present here. Let's for simplicity assume J, the group of type T. Okay, so T there means this one. Okay, and so to such J, you can find the Chevalier group, which will fiber by fiber have the same class, and that then which will be an algebraic group over spec Z. So I will call it like this: J over spec Z. So in what follows, I may somehow replace spec z by some open, but it doesn't change lots of things for us. So up to replacing sometimes, let me write it like this, may change spec z by b and open, the risky open. So sometimes in the arguments this may happen. So anyway, this j, you can even assume that it is in PGL n, some PGL n of z. You can find an embedding like that, and then you can look for the action on some not like this, but on some projective space this time. Okay, and then for the projective space, you can look for the quotients of the open with free action and the GIT quotient for the whole thing. So let me write it there. Sorry, I have to change in the blackboard on the other side. So I'm just writing what I've just said. Then J acts on some projective of some projective space. Okay, on P of some V. Okay. So let with free outside some S in P of V of high codimensions. This one can always find. So of high codimension S. Then let me put W, the quotient of P of V minus S by the action of J. This will be inside what I will call Y, the quotient of P of V of the whole thin quotient by J. Okay. So this is annotations. Then because of the way we defined the Chow groups, say of cohomology groups of the classifying spaces, then for any B in B, where B was probably an open of spec Z or spec Z itself, one can write HI, or maybe I start writing from here H4 because it's what we will be interested in. But anyway, you can take any I here, just fixing S big enough of W B with say the coefficients like that, because that's one we will be interested in. No, the action is free here. And then that's it. And you mean here? Well, sorry. Is it better?
The action can be free somewhere, not where the action is constant.
But you can still have a quotient by J, you mean, or not? Yeah?
Could that be also?
Well, I think that you can still... you can certainly make a choice so that this works, because...
But you want high codimension also.
Yeah. Because there is actually a very precise construction of this high codimension, so I think that's one that gives you the result. One can look afterwards precisely, but there is a really explicit construction. It's not like existence.
It's not a big deal because you can always take products, right? If you have something, let's say with a combination,
Yeah.
one you take n.
Yeah. That's true as well. Yeah. Okay. Yeah, so let me explain how to be projective in the end, okay? So for instance, just let's consider this part, and then et al. So this will be H4 because of the construction that we did, and we passed to this projective space, actually of B. So this quotient corresponds to first quotient by GM, and then the action of J, okay? ZL of 2. So actually, what we get is this group here, and that's normal because sometimes it's actually written in the beginning of Ekidal's paper that, for instance, for J equals to SL2, you don't have H2. So H2 is 0. So if you want to have a projective variety with that cohomology, you cannot do this. So you have to multiply anyway by GM. Okay. So this is for here. Now consider W like that will be the geometric generic fiber of this. Okay, so this is I'm trying to produce something projective rather than just this quasi-projective varieties. Okay, so one can look to this geometric generic fiber. One still have these properties here, and then let's try to produce something projective. So So this still has this compactification, which I will call Y, which is also YC. And let's take L linear section of W, meaning that you cut W by various hyperplanes, so you take enough of hyperplanes so that you have actually the intersection of W and L is the same one as Y and L. So I don't mean some subtle intersection here, but I just want to say that you want that this L doesn't that this L is disjoint from the complement of W and Y. So in this case, you see that intersecting like the W, you have something projective. Okay, this one will be projective. Just because of this equality. And then you want to compare the cohomology of these sections with the cohomology here. And indeed, because we are over C, you can do this, provided you check carefully the codimensions, but it works. So you can use what is called Ham's theorem in topology, which will tell you that actually that if we didn't make a mistake in the computations of dimension, that H4 of W, say with this coefficient Z, say Z or ZL or ZL, okay, this one will be okay as well, equals to H4 of W over L ZL2. Or if you don't like 4, you can start with I and then just choose also the coefficients as one should do. Let me keep this here because maybe I come back to these questions, and I will just continue writing here. So then at this point, we did something over the geometric generic fiber. Okay? And still we have our family, over B. So what we do, we just spread out L. Let L be a linear section corresponding to L over C. And let me call X, curvy X, the intersection of W and L. So we know the geometric generic fiber. So then let me take B, point of the base, such that the fiber is smooth. This one can do, and also I should have said that we are taking here, of course, the section so that the intersection is smooth. And so for any point such that XB is smooth, I'm claiming that then XB works in the following sense. So how will you make it work? So let me write a diagram. I hope I will succeed. So you have H4 of X over C with ZL coefficients, say. Then you can go to H4 of WC. Well, I don't remember. Maybe the maps are in the other direction, probably. Yeah, of WC. We say ZL, or let me check. It pass already to the final. No, sorry, with ZL coefficients, and then to finite coefficients. Finite, and then starting from this. So you know that this is the same as the cohomology of this classifying space, and inside this classifying space you have the elementary subgroup. Okay, so this goes to H4 of BZL cube ZL. This is because one has H3 in J. And actually, Yagita shows that here, so he computes here alpha. It will be ZL square, because there will be one factor coming from BJ and the one factor coming from the exceptional group. So still one has a class here. Let me call it beta, which goes to alpha with Q1 of alpha is non-zero. So it's done over complex numbers by Yagita, just showing that this map is somehow surjective. And then you have the specialization maps here, writing everything over the point B. Then you continue, go into the same H4 actually, because it's just a finite group. Well, this map has to pay attention because it goes another way around. But anyway, you check that the diagram is commutative somehow, producing here a class gamma. Let me call it gamma E inside, such that, well, it's geometric. Sorry, it's B here, such that Q1 of the reduction of gamma in Z mod L coefficients is non-zero. So this certainly should be written down carefully, but this is the idea of the argument. Okay. Yes?
So you have this like huge algebra acting on it. So is it reasonable to expect that the kernel of this action on a thought cohomology is exactly, the image of cycles, or you expect more abstraction?
No, I'm afraid I don't want any to say just like this, any expectation, any official expectation.
So there are no examples except for this.
Well, I mean, you really understand very well this one, so you can understand really what are the classes which are non-zero when you act by Q1 or something like this. So you have actually lots of them, but then so this surjectivity result is somehow subtle. Okay, so that's not really clear. And then, of course, the method works. I mean, certainly could work in a slightly different situation, because you just want to produce some kind of model which will be projective and with the same properties like here. Okay. Okay. So let me we still have like 10 minutes. So let me maybe give you just a very short overview of this positive result. Like this, we'll finish on some examples, not counterexamples. So a very short sketch of 2. So the first step would be the following. So let me change here slightly notation. So we are interested in this cycle class map, which is already over an algebraic closure. So let me call X the cubic, which is already over F bar. Okay, just not in order not to write it every time F bar. Then for such cubic, the first step would be so that there exists. So then there exists a Lefschetz pencil. Hopefully, Bruno recalled this morning. What does this mean? So and let me call U here the open, where the morphism, what I will call pi, is smooth. And then the first step would be to show it's really a homology computer. What? Sorry? Yeah. You can show that exists here in this case. Okay. So if you take alpha in H4 of X with the same type of coefficients, such that alpha goes to 0 by restriction to y, then alpha is actually 0. So this means that if somehow you want to show that alpha is the image of cycle class method algebraic, then actually it's enough to do this over y. So then the next step would be to investigate this fibration. So this is fibration over p over y. So on cuboid threefolds. And so for such fibration, you can construct here an incidence correspondence and a final variety. So let me consider f over u, which is by definition such that the fibers of f are exactly the Farner surfaces of y t for t and u. Okay, then as usual, you can consider the incidence correspondence here, which is I call here p q, and so this means that it's x L with x on a line, L big L with x on a line. Okay. So okay. So let's try to study that situation, and let me also make a notation. I will call J the relative peak 0 of f over u, and as far as I remember, it's actually better to take peak tau, not peak 0. But let me just for the talk put it just put peak 0. So with all this data, what we can do is the following. So we consider H4 of y with ZL two coefficients, and write just a Leray spectral sequence for this map. So this means that we go to H0 u of R4 P over star of this. And then actually this is just a map restricting to fibers. And then if we start with some class here, we can may assume that alpha goes to actually 0 here. And this is done by just, if not, modify alpha by alpha minus some line classes. There is lots of lines on X. So by modifying this, we can arrange. It's not difficult to see that the alpha maps to 0 here inside. Okay, and then meaning that alpha comes from the kernel of this, which is H1 of U R3 C pi, sorry, ZL2. So let me call this better. Okay. So now here this picture comes saying that you can produce a map to H1 U. So we change 3 by 1. It goes like this, and also 2 by 1 here. So there is no problem. So that's purpose. And then by studying the Kummer sequence for this variety, you show, so I think I won't give any details here, but you show that here you have a map here to ZL. And similarly, actually, it's really similar as for the, just in the beginning for the Brauer group and the codimension 1 cycles. Here, the co-kernel the co-kernel has no torsion. Okay, so it's just because of because you can continue this sequence. So what's going on here? So this J, this just big 0 FU, still it parameterizes some cycles here inside. And if alpha is in the image of the Chow group, so let me write in some color. So if we have CH2 X GL, some element going to alpha, then using by this incidence correspondence, so we get actually some section H0 UJ with CL coefficients. So just because if you take a codimension to cycle, then you look for the dimension what's going on, and actually you have here something inside. So this orange consideration tells you that if alpha is a class of algebraic, if an algebraic class, then you can have this you can find an element going here. So let me call here maybe gamma here the image. And now one uses that the co-kernel has no torsion. So let me write it again here. So let me call gamma here, and this map, connecting map, is delta. So if alpha is algebraic, then gamma is in the image of delta. And but by the work of François Charles, one knows that the whole Tate conjecture holds rationally for X, meaning that n alpha is algebraic for some integer m. Then together with the fact that co-kernel has no torsion and the fact that for n alpha we have that the element corresponding to n alpha is in the image, then that gives you that then alpha is in plus no torsion in the co-kernel. So alpha gives you an element in equals, okay, let me write like this, equals G of S for some S in H0 U J tensor L. Well, now now here we are somehow with something which is much more algebraic, because we have a section, a family of section of U over U of J. J is a peak 0, so it somehow parameterizes cycles. But, well, if you think to use, for instance, this incidence correspondence, we are here on the other way around, so it doesn't work at all. So the codimension, etc., it doesn't work. And one has to do much more analysis on this J. And just let me just resume this in a couple of words here. So S to produce an element. So let me call it, how I call it? In an element, not alpha, gamma. Gamma is not taken here, not taken. Okay, an element in CH2 X tensor ZL, starting from S, and an element which goes to alpha. So one should study this J more, and actually oversee the results of Markoshevich, Tikhomirov, and Druel, saying that J is birational to some modular space of some semi-stable torsion-free sheaves with some fixed Chern classes. So one can do this also in the family, or in the family somehow here. So use the study of moduli spaces. Of semi-stable torsion-free sheaves, semi-stable free sheaves, with so C1 equals to 0, C2 equals to L, which will be plus birational properties for J. So meaning that J will be birational to this modular space, and then having modular space, you can still make an argument to produce a cycle. So anyway, I think that my time is over, so I will just stop here, and if you want some more details, of course, I'll be happy to tell you. Thank you very much.